Thank you for the invitation. I'm going to talk about relativistic kinematics, GRBs, and gamma ray bursts. And of course, this is beginning not to work. Gamma ray bursts. Do I explain what cosmic rays are? Okay. This is based on an article that I recently wrote and on a long collaboration with Dado and Dar. Now, I will start with commercials, like every video on a computer. This talk will start in 6 transparencies. And what you see in here is a picture of a quasar, an active galactic nucleus, which is somehow spitting matter at long distances, distance of the order of 800,000 light years, before these blobs of matter stop and expand. This is the size of 10 galaxies or something like that. So this is a pretty energetic cannon. And when you look at it more carefully as an X-ray signal, astrophysicists, they always try to have you believe that they see what they want to see. So here they are trying to show you that this is something that is expanding with time. But if you take these lines to confuse you away, what you see actually is the same picture closer by, is that these things that are spat, this matter is not visibly expanding sideways. It is just proceeding, perhaps becoming less luminous, but it's proceeding. This is a picture of the same object. The black, the gray scale is for is X-rays, and the red contours are contours of radio emission. And all I'm going to do today is essentially to interpret this picture as matter that is moving, colliding with other matter, producing, among other things, electrons. These electrons generate a magnetic field in which they themselves radiate synchrotron radiation and produce this big blob of radio signal. Now, this is to remind you of an old friend of most of us, which is a supernova that was seen in the Magellanic Cloud some years ago. And what you see in this picture, taken with speckle interferometry, is that it did emit at a certain point 2 balls of something which is shining in opposite directions and moving at relativistic speeds. So supernovas do produce this thing that I will call balls. Now, this is the end of commercials, so I now can skip the video and show you that in our galaxy there are also small limitations of large quasars, which are called microquasars. This is also a black hole, which has an accretion disk that sometimes collapses into the object. And then this object, this black hole, emits 2 opposite balls of matter, also at highly relativistic speeds, gamma factors, Lorentz factors of order of 10 or so in this case. Now, the emission is perpendicular to the disk in the same way as if you drop a ball of matter into a surface of water, the water closes up and up. No, the photograph doesn't show the disk. What one knows is that the X-rays from the disk disappear when one of these emissions takes place. So the disk gets eaten. Now, I'm going to superimpose this object on what a supernova may look like right after the explosion. Supernovas pass periods in which they spit a lot of matter before they finally die. When they die as a supernova, they emit radiation that illuminates this matter. So you have a sort of corona of light around the object, and if you superimpose these blobs of matter going through this light, what's going to happen is that electrons in the matter are going to Compton scatter the light into much higher energies. That's called inverse Compton scattering. And this is called glory. So the glorious light is inverse Compton scattered by the cannonball's electrons. Now, suppose you are an observer and there has been an object spat in a direction with a large initial Lorentz factor gamma 0, and you are at a certain angle from the jet. And for gamma 0 much larger than 1, which is what we shall study, and observation angles much smaller than 1, the Doppler factor by which light from a moving object is boosted to higher energy for you is this simple formula in here. This should be a gamma 0. Now, the observed luminosity, the number of photons per unit angle, is the one that it would be if the moving object was at rest, multiplied by delta squared. So this is a very forward beam angle, and in our model of these things, we can extract a distribution of Lorentz factors of the original cannonballs spat by supernova, and this is a logarithmic plot. So you see that the original Lorentz factors are of the order of 10 to the 3. So the beaming due to this delta is very, very extreme. This is 1 degree, and you see that this is the delta not squared. With delta squared, it's even more so. You have a very, very narrow beam of light that has been Compton scattered by electrons in your direction. Now, one cannonball in your direction corresponds to one gamma ray burst pulse. The gamma ray bursts are happenings in the sky that send to you a one or a few bunches of gamma rays of order 1 MeV energy. These are 2 gamma ray bursts dated as written, and this one only had 1 cannonball, so you see 1 pulse. This had 2 cannonballs, so you see 2 pulses. It's relatively simple, and on the basis of the simple Compton scattering, you can actually figure out what the energy and time distribution are of these things, which are plotted here, the theory on top of the data. And this is simply Compton scattering. Now, it implies this very simple theory of how the gamma rays are made implies correlations that are very tight, as if all the properties of GRBs were fairly standard candle-like, but for the viewing angle. That is, of course, random. Now, you have, for instance, the peak energy of the gamma rays in a pulse, and that is the energy of the Compton upscattered photons times the Lorentz factor times the Doppler factor divided by the redshift factor. And the isotropic equivalent energy, how much energy the thing would have emitted if it wasn't bent, is gamma delta cubed. So the most probable missing observing angle, which is about 1 over gamma, the peak energy is related to the square root of the isotropic energy, and Farov axis to the third root of the isotropic energy. And that's what you see in the data. Over very many orders of magnitude, 5 or 6 orders of magnitude in here, there's a correlation between the peak and the isotropic energies, and which is just dictated by the fact that you're assuming this is simply Compton scattering. And for the Farov axis GRBs, where the rule should be 1/3, this is what happens observationally. And also for short hard bursts, which are not due to core collapse supernovae, but for another type of supernova, those are also seen close off axis because they are not very luminous, so you have to be lucky. And the rule is also satisfied. So close to the axis you have a GRB, far away from the axis you have an X-ray flash, so smaller energies, and short hard bursts, which are also high energy but last less, are there. Now, there is plenty of such correlations, about 10 correlations, which are simply based on the kinematics of Compton scattering, and all of which, I'm not going to go through the details, are perfectly well satisfied over very large ranges of energy. Even you can go into a disk and relate the energy of the pulse, the time distribution of the pulse to the energy of the pulse if you divide it into different intervals, and all these things, simply based on Compton scattering, are very well satisfied. Now, let me take a cannonball, this object which is moving through the interstellar medium, and put it at rest. Then we will see the particles of the interstellar medium, for instance, the nuclei in the interstellar medium, come to it and be scattered. We'll see that these things have a magnetic field in them. I'll go to more details on that. And when they are Compton scattering, we shall see they become cosmic ray nuclei. The same for electrons will become cosmic ray electrons. But what I'm going to emphasize at the moment is the synchrotron radiation of these electrons in the magnetic field, which is what is called the afterglow. A gamma ray burst doesn't just happen and disappear. There continues to be radiation from the same spot at lower energies, and that's called the afterglow, which may be measured during years of time. Now, I'm emphasizing that this is what I'm going to talk about now, and it's also very simple to predict what synchrotron afterglow should look like as a function of time and energy. And that turns out to describe the afterglow very simply. Now, what I'm going to emphasize now is that this theory of gamma ray bursts is extremely predictive, and thus extraordinarily hated by the experts on the field. It cannot be accused of being popular because it works. And in astrophysics, you don't have to fight against astrophysics. You have to fight against astrophysicists. Now, it's relatively simple, always in these simple terms, to figure out what the dependencies on frequency and time of the afterglow of a gamma ray burst due to a cannonball emission. That was the gamma rays of a certain gamma ray burst. And let us now look at the afterglow of this same object in an R band, that is to say, light around red color. And you see here the measurements for the first 6 days. This is a few seconds, 50 seconds, and this is days now. So the gamma ray burst took place here at the very beginning of this plot. And you see the afterglow in red light due to a cannonball 1 and a cannonball 2 that are put here. Now, we are so confident in our theory that we were able, in this particular case, to predict that at a certain date, the day 10 after the supernova, after the explosion of the observation of a gamma ray burst, they should see a supernova which produced it. And that's the data, and you see here that precisely on the date we predicted, they saw a supernova. This was at a time where the official theory was that gamma ray bursts were not produced by supernovae. But we were confident enough to predict even the date in which a supernova would be discovered. Normally, you know when a supernova is going to be discovered with an error bar of 10 million years or so. This was a few hours error bar. And why you know this was a supernova from a certain point, the light that you see? Because the spectrum of a supernova is very different from this. And this corresponded, this light which is shown here in only one color, had the light distribution of a supernova. So that was the prediction of the fact that duration gamma ray bursts are made by supernovae. Now, the afterglow changes with time in what is called the Faribault model, the standard, so-called standard model of gamma ray bursts, in a certain fashion with time. And this is, again, light of a given frequency. And the CB model had a prediction which was very daringly different. You see, we had a few points to think about at the time, and only one case in which such a thing could be measured, which was this one. And at a certain moment in the development of the observations, a satellite called SWIFT discovered what they call the canonical X-ray afterglows, which happened to be what was precisely the prediction of the cannonball model. Of course, this was also not recognized, but was a fact. Let me go now to a very simple physics exercise that you should your students do. Suppose you have a supernova, it has exploded, it's emitting light that you see, and it has emitted also a cannonball in roughly the same direction where you're sitting. By the time a photon of light has moved to here, since this cannonball is moving at a Lorentz factor of maybe 1,000, it has almost caught up with the light. So when it emits light, the time difference between this light and this light are very small. So if you divide the transverse distance that you have seen this thing moving in the sky by the interval of time, which is shortened by the fact that this object is also advancing, you see an apparent superluminal velocity. So you measure that in the sky this thing is moving as if this thing is moving relative to this point, as if it was moving at a velocity higher than the velocity of light, although it isn't flying faster than light. So again, in this gamma ray burst that I have shown you in a moment ago, we had a prediction which was for the distance. It had two cannonballs, and we had a prediction for the distance at which the two cannonballs will be seen in the sky as a function of time. This was our prediction. The line was our prediction. These are the data by Taylor et al. And Taylor et al. Concluded on the basis of this dramatic difference between theory and observation that the cannonball model was excluded. And they published it, including in the New York Times. And that's a sort of interesting story, but it's long and I won't tell you. And they also decided that one of the two spots they saw in the sky, in the afterglow, which was 20 sigma evidence, was not predicted, was not understandable in the standard theory. But that's all they said. That didn't disprove the standard theory, that there was something with 20 standard deviations contrary to it. Now, I'm now going to move. This was only to give you the impression that there is some basis for believing some aspects of this very simple cannonball model, which is essentially inverse Compton scattering of light. Let me move to the standard model of cosmic rays. There is a standard model of cosmic rays whose implementation is a computer program called GalProp. And it is employed precisely as the standard model of particle physics is employed at the LHC as a background for possible discoveries of new physics. All they do, these people, is exactly what we do at the LHC, with one exception. And that is that the cosmic ray model inputs are totally unbelievable, and that the model must be modified every time the data become more precise, and that it never made a correct prediction. Now, it's interesting in the field of cosmic rays that there has been in the past history, the 100 and something years of history of cosmic rays, only one prediction that turned out to be right, which is not very many for 100 years of physics. And that is that an energy of a cosmic ray bigger than confinement energy of that cosmic ray nucleus of charge Z in our galaxy, the cosmic rays must be extragalactic because the galaxy doesn't accumulate them. And if you figure out what the Larmor radius is for a typical magnetic field in the galaxy, which is 5 microgauss, this is what it would be for a proton. The confinement energy for a nucleus of charge Z is, figuring this out, some 3×10⁹ GeV. And there happens to be in the cosmic ray spectrum an angle where the slope becomes less fast at 3×10⁹ GeV, which is precisely the prediction for where protons would not be confined any longer. That was a prediction that was made by my friends Pepe Cocconi and Phil Morrison in 1950-something. And it turns out to be the only correct prediction ever having to do with cosmic rays. We have learned recently that this prediction is supported by new data from Auger, who, for cosmic rays of energies more than about twice the confinement energy for protons, there is a large asymmetry of arrival directions of these cosmic rays. There is an observed dipole asymmetry, which is not pointing to the galactic center. So there's an accumulation of sources in some direction of the sky, from which the very high energy cosmic rays, which are extragalactic, are coming to us. So this proved Morrison and Cocconi correct. Now, this is to come back to the model. There is a supernova that collapses. These stars have a very large angular momentum, so maybe they don't only make a central compact object, but also a torus around it of accreting matter, which collapses like in microquasars now and then, and every collapse of this object produces a cannonball on one side and a cannonball on the other side, and when they traverse the ambient light that has been illuminated by the supernova itself, they Compton upscatter photons, and if you see them close to the axis, it's a gamma ray burst. Far away from the axis is a X-ray flash. Now, the CBs, as they travel in the galaxy, they collide with the interstellar medium and are going to decelerate in the galaxy and its halo. And I'm showing again something that I've plotted before, which is the production of cosmic rays and the synchrotron afterglow in the magnetic field of a cannonball. Now, I'm going to say that cannonballs scatter ions and electrons and make them into cosmic rays. And the question is, how does that happen? Now, here's an observation. The energy density of cosmic rays in our neighborhood of the galaxy, computed from the observed flux of cosmic rays as a function of energy, is about 0.5 electron volts per cubic centimeter, which happens to be precisely the energy density in magnetic fields in our neighborhood in the galaxy for a typical magnetic field of 5 microgauss. So these two entities, the cosmic rays and the magnetic field, are in equipartition, energetic equipartition. That's not very surprising because one makes the other and the other contains the first. And in fact, there are simulations of collisions between plasmas of protons and electrons at relativistic relative velocities, and those are seen to produce magnetic fields, vorticity, all these things that we've been told in the previous picture are made if you have two colliding plasmas. So a CB cannonball in motion in our galaxy is going to emit gamma rays. By the way, the typical baryon number or electron number of these objects as we extract from the data is 10 to the 50. That is to say the mass of Mercury. This is due to inverse Compton scattering. And this is such a tremendously energetic beam of photons that it ionizes completely the interstellar medium on its way. Now let us look at this object that was moving relativistically with an initial Lorentz factor of 1,000 or so in its rest system. Well, it is going first as any decent plasma going to expand, any decent relativistic plasma, at the velocity of sound, relativistic velocity of sound, which is c divided by square root of 3. And that means that in a few seconds of observation time, it's going to become transparent in the sense, or collisionless, that a proton going through it won't have a proton-proton collision because this density is too small. It will only interact with the magnetic field of this object, which is being generated in entire analogy to magnetic field of the galaxy by the cosmic rays themselves, and that we assume to be in energy equipartition with the, in this system of reference, incoming interstellar medium particles, nuclei of charge Z and mass A, and electrons with a certain number density. So I'm going to argue that this will become a cosmic ray electron while it is emitting synchrotron radiation, and that the other thing is going to become a cosmic ray nucleus. Now, the cannonball theory of cosmic rays has a series of predictions: the normalization of the flux, the spectral features, the knees, the ankle, the endpoint, the slopes, the chemical abundances of the different cosmic rays, the confinement, volume, and time in the galaxy. These are all the properties of cosmic rays, and they are all predicted by one mechanism, the one I just described, at all energies. And they do that with only one parameter for cosmic ray nuclei that I will not need to use today, which is the proton flux above or below the ankle, and one parameter, which I will choose freely today, for the normalization of the flux of electrons. Now, the theory, like our understanding of the cosmic background radiation, there is a certain fundamental theory and a lot of priors, information that you get from independent observations. In this case, this is a list of priors. I won't go through them today. For instance, I've just mentioned one, the flux normalization of the cosmic rays, which is related to the supernova rate in the galaxy, which we know to within a factor of 2 or 3. The important priors today are the galaxy's magnetic field, which correspond to a confinement time in the galaxy of the order of 10 to the 7 years, and that increases with a negative power of the charge and inverse to the momentum. This power is measured in cosmic rays via the study of secondary cosmic rays to be about 0.6. So that is the ensemble effect of the confinement magnetic fields in the galaxy. And if you have a theory of what the flux is of cosmic rays as a function of energy, then you have to hit it by this energy to the minus beta confinement. Momentum and energy are the same at the high energies I'm talking about. You have to hit it by the confinement time power, because the cosmic rays that are of low energy will spend more time in the galaxy and therefore accumulate more than the high energy ones, which are faster in escaping. And the other prior that we'll be interested in is the measurement of the cosmic ray, of the interstellar abundances of the various elements in superbubbles, which are regions where many supernovae have exploded in the past, and they have these measurements an order 10% error. Now I'm going to open here a parenthesis to see whether we're moving in the right track, and to look at our predictions of the time of the abundances of the different elements in the cosmic rays. Now take an object of a very high mass, baryon number 10 to the 50, which is moving relativistically very fast, and it collides with a poor little thing, which is an ionized object in the interstellar medium, an ion with mass m. Now let's look at this in the cannonball rest system. It is the ion that is coming with a very large Lorentz factor. They are going to ooze out, diffuse out of the magnetic field in the cannonball itself. Some of them, the maximum possibility for their outgoing Lorentz factor is the gamma with which they came in. And if they happen to be, this is also a measured zero case, if they happen to be boosted back, not isotropically in this system, but in the direction in which they came in this reference system, then they have a Lorentz factor gamma also. Now, if I boost this object back to the reference system where it's moving with a Lorentz factor gamma, then the energy of this outcoming object is proportional to its mass with a Lorentz factor 2 gamma squared. That's the result of the Lorentz transformation. So that, since the gamma zeros are for order a million, this is of order 2 million times, 1,000, this is of order 2 million times the mass of the particle that has been scattered. This is the limit, the possible maximum energy in a distribution that I shall compute. And it's independent, in terms of gamma, it's independent of the mass, and in terms of energy, it's just proportional to the mass. So this is a relativistic racket of a tremendously high efficiency, because it boosts the light particles to twice the Lorentz factor squared of the particle that kicks them. Now, this is a very important thing, so I'm sort of emphasizing it. One can do a calculation of everything I just have said, which I will not have the time to do today. It's relatively simple. I'll flash it later. But the predicted distribution of the Lorentz factor of the cosmic rays produced this way is the Lorentz factor to a certain power that turns out to be 13.6. You have to hit that by the confinement extra power, which is 0.6. So the prediction is that the slope in gamma of a cosmic ray energy distribution is 2.77. If you make now a very simple change of variables, that the energy is proportional to the mass of the object, its atomic weight times gamma, you can obtain from this very simple calculation the expression for the fluxes as a function of energy. They are proportional to the number of particles that have been upgraded in energy times a to the b theta minus 1. The minus 1 comes from this transformation. The energy to minus b theory being this. And at a fixed energy, which typically is taken to be 1 TeV for this type of comparison, the number of cosmic rays in the flux of the object A is its density a to the 1.77. That's a very large number. For instance, if I put 56 in here for iron, that's 2,500 or something like that. So if you take the abundances in a superbubble measured for the various elements here relative to hydrogen, and you multiply them by this number, you get one of these two curves. I don't know which one it is, and the other one are the observations. So this is a fantastic prediction for the observed relative. Antonia, this is making me rush, so I won't read this. I'm telling you that this theory works from the lowest energies to the highest energies. But let me get to my conclusion of a decade ago. This is not today's conclusion. It was that the challenge of cosmic ray production has been met, faced, and overcome almost to my entire satisfaction. Now, why did I say almost? Because all we were saying at the time, 10 years ago, were predictions. But there happened to be now new data. So these were the data. I know this is unreadable, so let me tell you what it is. This is data which are 10 years old. The vertical scale is the logarithm of e to the 2.5 times the flux, and the horizontal scale goes from 1 to 10 to the 8 GeV, and it's also logarithmic. And so these were the independently measured fluxes of protons, helium, and iron. You see that there was something here which they call the proton knee, which was significant. In the case of helium, there was also something, but you don't know whether it is significant or not. And in the case of iron, there was no conclusion to be made. But the data in this domain have been improved a lot in the past 10 years. And well, I happen to be telling you something here which I will be fast. That is that in order to do the calculation that I told you of what the flux is as a function of Lorentz factor, I have to figure out how the object, the cannonball, is expanding as it travels in the interstellar medium. It's eating some of the interstellar medium, so its mass is increasing with a certain pace, and its radius is increasing, but it's almost flat over all of its motion through the galaxy. And this calculation is what a cunning referee referred to as, it is almost Baron Munchausen, by which he meant, no doubt, that was a series of well put, intriguing fabrications. But if I was and not the referee, I would say it's a list of intelligent arguments, because something has to explain the fact that these cannonballs are observed not to increase their size with energy. This is a calculation. I'm not going to do it. It's a calculation of the fact that the slope of the source distribution of cosmic rays is 2.17. And the important thing is that this flux ends for a particular cannonball of initial Lorentz factor gamma 0. It ends at 224 10 to the 6 for the factor by which the mass is converted into energy. Now, the only prior that I'm going to use today is this thing that I showed you, which is the measured distribution via gamma ray bursts of the initial Lorentz factors. And if instead of having one cannonball, I have a series of cannonballs, I have to do the sum over all cannonballs, that is to say over their distributions, of this theta function in here, which is just this integral. So there's going to be a knee in the cosmic rays, which multiplies its energy dependence by this distribution integrated, and it only depends on the mass of the cosmic ray and nothing else. So if I plot it for iron or for protons, it's going to be the same distribution in a log-log plot, only transported by a factor 56, which is the mass ratio of iron to protons. If I do it log linear, it will look slightly different, but it's the same distribution actually. Now let's go to the data, to the recent data. This was our prediction for what the slope should be years ago. And let me now multiply it by this cutoff factor, which is the knee. The prediction is that there should be a break. That's what we said years ago, at 224 times 10 to the 6 the proton mass, and there it is. And that's how it looks like if described by this function here. Now there's a little extra thing in here which I will not explain today. For helium, the data have improved, and there is also evidence for an E at precisely the right position, that is to say 4 times higher energy than that for protons, and this is just the same function now for helium. I'm not going to talk about the low energy cosmic rays today. Now for CNO, this I must admit I don't understand the data. The best data are these, and they don't look like the predicted knee quite so well. But the iron knee, which is now the best measurement, fits precisely through this thing in here. And that means that in going from protons to iron, we have seen this curve be always the same and move by a factor 56 in energy. The dotted line would be the result if it was the charge of iron that mattered and not the mass of iron that mattered. That seems to be excluded. But it wouldn't be so excluded if I used this as input and then predicted the protons, because the protons are less well measured. However, the indication is very strong. The Ni is there, and it works well. Now, the strong test, and with this I'm finishing, of this kinematic Nis would be the electron flux, because it is now measured to higher energy and much better precision than it was 10 years ago. And the ratio of the masses of the electron and the proton is what is written in here. It's a very, very large or very, very small number. Therefore, this position of the Ni is an extremely strong prediction for the case of electrons, in which this ratio is very different from 1, but the ratio of charges is 1. And for electrons, I must remind you that the slope of the electron flux is that of the proton flux plus 1, because electrons lose energy, giving rise to this prediction very efficiently at the energies I'm going to talk about by scattering on the interstellar light and synchrotron radiating in the magnetic field of the galaxy. So I'm going to be honest and tell you that the electron flux is not predictable in normalization, but it is in shape, the shape I have just described. Now, these were the data about 10 years ago. There was no Ni, and they extended to about 2.5 TeV. Now, another thing that I have warned you is that I am predicting in this talk the primary electron flux. But the highest energy measurements now available are for the sum of positron and electron fluxes. So I need the secondary electron plus positron flux to add it to the primary and have a theory of the complete flux. The electron plus positron flux, the simplest and most sensible assumption is that it is secondary. It is produced by cosmic rays hitting the interstellar medium, producing pions and kaons, which decay into muons, which decay into electrons. All these things are very well understood, and in particular the fluxes of mu pluses and mu minuses are also well measured. And that very simple theory, completely standard, based on what you could measure at the ISR, it's a little bit modern, in any other modern accelerator, gives you this flux of positrons. The flux for electrons is 70% the flux for protons, like the ratio of mu pluses to mu minus, which is reminiscent of the fact that these two objects colliding are positive, and therefore they prefer positive charges in the final state. Now, this is a couple of years ago, the data for the electron flux times E cubed as a function of energy. And what you see in here is our prediction for the primary electrons, about which I talked today with its beautiful Ni. The secondary electrons plus positrons, they look like a lot, but this is a logarithmic scale. And then the sum. The sum is in red for the total, and that would be the case if there was no primary electron break. So even a few years ago, there was evidence for the existence of a proton Ni. Now, this is the most recent data plotted here in order to confuse you in a linear log plot. And what you see in here are a bunch of experiments that are recent, and then a slightly older experiment in green, which is AMS. Now, this is what I just told you. This is the primary electrons. This is the secondary electrons and positrons. You can now see that it's relatively small up to the Ni. This is the total in red. And there should be a break in the electron spectrum, which is the mass of electron divided by the mass of iron times the electron break. And if I read something I wrote explicitly 10 years ago or so, I say there should be a Ni at 2.3 TeV in the electron spectrum, and there it is, your Ni at 2.3 TeV. Now, that would be the prediction without a break, and this is the prediction with a break. Now we have made an extrapolation of 5 orders of magnitude, and the origin of the Ni as a purely collisional fact is strongly supported by the data. By the data, with the exception of AMS. Look that AMS disagrees with the all other 3 or 4 experiments. So what can I conclude when this is the situation? Well, I cannot conclude anything, but I could quote Eddington, who said that never trust an experiment until it has been confirmed by theory. And EMS has not been confirmed by theory. So this is my last transparency. Cannonballs, initially moving with large Lorentz factors and kicking the interstellar medium as they move, trivially predict the cosmic ray niche. And that's the place where I stop. Thank you. Yes, Remo.
Very interesting. Necessary to understand how this fits with our understanding of gamma ray burst.
Yes.
And there is only one point recently discovered, is that in a gamma ray burst you have 2 different components. The prompt radiation, which is the one that you were showing, that indeed is confirmed that has gamma Lorentz factor of the order of 10 to the 3, like you speak. And then there is the afterglow. This is the new result. The new result is that the afterglow is almost non-relativistic. Therefore, I just call your attention on this fact.
No, this is not a fact. This is an interpretation of the observations.
Yes, yes.
Which is different from a
Yes.
fact.
Yeah, well,
Okay.
yes, it's a fact that if you, anyway, there are the 2 components, there are clearly 2 components.
Yes.
One of the afterglow at very Lorentz gamma factor of the order of 2, and the prompt radiation at 10 to the 3. And it's very interesting to see how your consideration fit with.
No, my considerations don't fit that fact. They predicted precisely the variety of observed afterglow properties in time and energy.
I just want to call the attention on this fact that we have.
Okay. This is not a fact. This is what you're saying, which is different from a fact.
Alvaro, this was a very wonderful talk, as always. I just have one serious question. I heard the word, I didn't understand all of what you said, but I heard the word canonical, and I heard the word cannonball, and which are pronounced similarly, but your conclusion seems to be that these are more antonymic than...
Sorry, these more?
These 2 words, cannonball and canonical, are more antonymic than synonymic.
Well, they come from, they have different authors in this particular respect. Cannonballs is something that we call these objects, and canonical is the expression used by gamma ray burst. I was going to say theorists, but in this field there is no distinction between theorists and experimentalists. The papers are written by the theorists who interpret the experiment. And in their language, canonical behavior of an afterglow is that it drops very fast and it becomes flat and then it drops again. The first drop is not achromatic, the second one is. And that's what they call the canonical behavior. They could have called it anything else. I don't know why canonical. Canonical in the sense that most gamma ray bursts show afterglows with that sort of properties.
Okay, thank you, Alvaro.
Thank you.
Thank you again.